Hi, my name is Tu, and I'm a student from the University of Toulouse, France. And thank you for joining me in today's session at the Xen Developer Summit. I would like to present our recent work, which is a solution for replacing one kind of hypervisor with a completely different one in a short period of time. So first, I'll be giving you a short overview of the solution, and then later I'll go more into the technical details as well as some of the future directions that we would like to take our solution. And at the end of the presentation, there'll be also a short demo of our solution, so you can stay tuned for that. First of all, let's go into our idea. So it's actually quite simple. In our solution, we aim to transplant the running VM that is running on one hypervisor to a different one. For example, you can imagine moving a running VM from Xen to KVM or vice versa. And the idea to do this is to do this without disturbing the VM or without requiring it to reboot. Another goal of our solution is that we'll be able to do this transplant of the VM on the same host or between different hosts. So in other words, it's the combination of live hypervisor replacement and live migration. And this solution, we call this solution HyperTP for hypervisor transplant. So by the way, our talk today is going to be a more technical overview of the paper that we introduced at EuroSys this year with the title of Mitigating Vulnerability with Hypervisor Transplant. So if you want to look into more numbers, more evaluations of our work, you can check out our paper on ACM, which is free to read, and I'll be linking that later. So here are the few reasons why you might want to transplant the running VM between different hypervisors. So first of all, for example, you can use it to, let's say, escape hypervisor vulnerabilities. For example, if your hypervisor has a security flaw, normally you would have to wait for a security patch. But instead, you can think, why not switch to another hypervisor that you effectively have escaped the vulnerability without having to wait for the patch? And you still have the choice to return to your original hypervisor once it's fully patched. And naturally, you can not only move from one kind of hypervisor to another. You can imagine using this transplant process to upgrade your hypervisor from an older version like Xen 4.11 to Xen 4.12, or the same thing to the Linux kernel that is running your KVM virtual machines, for example. So you can also use it to, say, upgrade your underlying hypervisors. And another use case is that if you're tired of your existing hypervisor, so if you want to use another hypervisor for hardware support or for some fancy features, or if you just want to switch vendors, then you can use hypervisor transplant to gradually migrate your system without having to bring down your VMs. And there are also other use cases that I'll be discussing later in our future work section. So like what we said before, at the core, our solution is a combination of two approaches. One is that you directly replace the running hypervisor with another while preserving the VM on the same host. And we call that in-place hypervisor replacement or in-place hypervisor transplant. Another approach is that you migrate the VM that is running on the source hypervisor to a different destination hypervisor on another host. And this is very similar to live migration. So we just call that approach migration-based transplant. So regardless of the approach that you take, either in place or migration-based transplant, we are using a common workflow which consists of 5 steps. So firstly, you preserve the VM state and memory of the running VM that you want to transplant. And then you suspend it, which are steps 1 and 2. And next, you transplant the VM to a new hypervisor, either using the in-place technique or the migration technique. And once the transplant is done, you restore the VM states, and then finally you can resume its. So that's the main 5 steps for both of the approaches. So for our actual implementation, we based it on Xen and KVM, of course. For KVM, we focused our implementation on top of KVM 2 because it's a very simple and very compact wrapper over the KVM API. And also because we wanted an implementation that's very different from both sides instead of, say, just relying on QEMU on both sides in the end. For in-place replacement, we implemented it from Xen to KVM and from KVM to Xen and as well as from Xen to Xen. So like I said before, with this Xen to Xen implementation, you can also use it to upgrade from one version of Xen to another. For live migration, we also have an implementation for migrating VMs from Xen to KVM. And all four of these implementations together, they are around 8,500 something lines of code. And of course, of which around 90% of them is in user space. So there is very little impact to the existing hypervisor kernels. And I would say that it is a kind of a flexible implementation that would minimize the security impact of our solution, which is a question that we had before quite a few times. Like how much does this kind of solution affect the, let's say, the TCP of the system? Um, so next, let's dive into how we implemented the solution in detail, and I'll also talk about a few of the difficulties that we had along the way when we were doing this kind of system. So first of all, let's go into the saving of the VM. Something we really like about Xen is that it already has a well-defined format for saving state of HVM VMs, which is also really easy to understand and work with. So we just took that format as the common format for our solution. So when you save the devices of the VM, for the Xen side, the work is quite simple. And for now, we save the HVM state of the VM. On KVM2, though, it's a bit more tricky because it doesn't understand the state by default. But all that needs to happen is just you call the correct KVM IO controls, you get the VM state and translate into the form that then will understand, so that you'll be able to restore it on the other side. And that alone takes care of the main platform devices that are critical to the VM's operation. But in this step, we also have the network interfaces or storage devices of VMs, any of the other virtualized PCI devices, because the details of the virtualization of these things, they vary quite a lot between hypervisors, and that includes any PV features for now, you can say that. For Xen to Xen transplant, it's quite simple, so I'll be describing it later. So let's go to the next slide. The next step is to take care of guest memory. In the case of migration, for example, we use the same logic as VM migration, so that's quite easy. But for the particular case of in-place replacement, ideally we try to keep guest memory pages in host RAM so that these pages can be reused by the next hypervisor. The first step that we need to do is to enumerate these pages and their location in physical memory. On Xen, we decided to resurrect the NVIDIA hypercore patches to do this. On KVM, it's a little bit easier. Because we can use PageMap to do this for us. But anyway, after we know the mapping of the guest pages, we construct an in-memory file table structure to keep track of these pages and to represent each VM's memory as a separate file. And we call this the PRAM structures, which I'll go into detail in the next slides. For the particular case of in-place Xen to Xen, we merge this step with the step of saving a VM state. And we do this by modifying XL save, and instead of saving directly the VM memory to disk, we just place a placeholder marker that tells the hypervisor to find the memory in PRAM. The way we construct PRAM is that, first of all, we allocate some temporary memory, and then we define some regions of physical memory that cannot be preserved in host, and then copy any VM memories that's living there into the temporary region. We finally use the remaining temporary memory to construct the PRAM table for each VM. Basically, we do this step to make sure that the step of KExec will not accidentally erase some of the VM pages by accident later. For the structure of the PRAM tables themselves, we adapted it from the one that was used in Vladimir's PRAM patches. We made a few modifications so that the PRAM chains could be constructed in parallel for each VM, and also to support bigger pages like 2 megabyte pages on x86, for example. So this is the structure of the PRAM table. It starts with a PRAM pointer value that points this is the pointer that points to a chain of root directory pages, which is colored red here. Each root directory page contains, again, 5 pointer entries that themselves point to 5 info pages, which are colored in green. The file info pages are like inodes, and they contain the metadata for the VM's memory file, like the size, the file modes, file names, etc. And each of the file info page also contains a pointer to a chain of nodes containing page entry. Each node is colored blue here. And each page entry finally is a guest physical to host physical mapping of a memory page, so that later this mapping can be restored in a new hypervisor. So now that we have saved the VM, we proceed with the third step, which for migration is just like normal live migration. And for in place is to replace the running hypervisor. In this, just do a kexec into the new kernel and pass it the preamp pointers that we produced in the previous step. Um, Again, there are a few hacks there are a few things that we encountered during the kexec, so they're pretty small things. So we had to add some hacks into this. We had to change a couple of things like memory information when your system is UEFI and doesn't have a CSM, or you had to give Xen the correct ACPI RSDP, or there were some changes in the MBI generation, for example. We also took the opportunity to optimize the process of booting a new kernel a bit. Like when you have a RAID card in the system, it takes quite a bit of time to boot after the kexec. So we made some changes to skip the to speed up the reinitialization process, which saved us a lot of time. Is this step, because you see that later kexec part is actually the most time-consuming part of this problem. So now that we've entered the new hypervisor, we have to start the step of restoring the VM. So we added code in KVM2 to map the state of each VM between Xen and KVM, and then we restored each device with the corresponding mapping, which you can see in the table here. During this process, we also had to make sure that the structures of the virtual devices on both sides match up with each other. For example, we had to make sure that the number of IO epic pins on both sides match up, and to make sure that devices like virtual clocks would continue to function after the transplant. We also did some changes to, for example, to fix the PCI bar emulation on KVM2, or to expose some features in CPU ID that we wanted to use for KVM to Xen in transplant, etc. For the memory of the VM, the process here is quite simple. So in the case of in-place transplant, the new hypervisor parses the PRAM structure and detect existing memory regions, and protect them from being overwritten by accident. For example, on Linux, we use the existing code that is provided by the PRAM patch. On Xen, we create a virtual domain and assign these pages to this virtual domain so that it cannot be accidentally allocated by other VMs, for example. We also present them to the new VMs being restored. For KVM, for example, we just present it as a RAMFS file system. So KVM2 can just mmap the file and have the memory ready for use. For Xen, we added some new hypercores to help Xen traverse this file system and to assign these files to the memory of the domains that need to be restored. And that's everything for at least the steps of hypervisor transplant. So let's look into some of the numbers. So since we have quite a few different cases of hypervisor transplant that we need to examine, so here we go into details, the case of Xen to KVM transplant. Here we have a figure that tells you how long each step of the process takes for a VM of 1 vCPU and 1 GB of virtual RAM. So you see for this very basic case of live transplant, the process only takes 1.7 to 3 seconds, depending on the kind of machine you're using. For some devices, though, it takes more time to restart. For example, the network card takes around 8 seconds before the connection is resumed. But like I said before, we also implemented some changes into the Linux kernel to allow this a faster initialization of devices, which, for example, for the RAID card, like I told you, it saves around 30 seconds of time of the process. So here you have a very small breakdown of each step, which PRAM here is the initial asynchronous construction of the PRAM metadata pages. Translation is, you can say, the step where you actually stop the VM and complete the construction of the PRAM. Reboot is, of course, rebooting with kexec, and restoration is the step where you resume the VM at the end. And there's also another column for network, which is the total time it takes to start the network card and to make sure the networking on the VM starts working again after the transplant. So that's it for the basic numbers, but also I have some numbers, for example, to compare the two solutions. Here I have a figure of Redis performance under in-place and migration to show the impact of the two solutions. The left side is comparing in-place transplant to normal VM running on Xen without any disturbance. So we see here that the process starts and then 9 seconds later, which is a small gap over here, the VM resumes, and afterwards you don't see impact to Redis performance before or after the transplant. On the right side, though, with migration, you can see that regardless of whether you are doing Xen to KVM or Xen to Xen migration, the performance is pretty much the same. In this case, the Redis server is impacted by the migration for around 76 seconds, as well as a short period of downtime before everything goes back to normal. So we can see how a solution like in-place transplant can speed up the process of patching of a data center because you spend a lot less time on migrating the host, and all of the VMs get transplanted at the same time without consuming extra network bandwidth, and doesn't have this kind of long periods of impacting the performance of VM. So that's just a few notable numbers of our solutions. If you want more details on evaluations, you can check out our paper, which I'll link into I've linked into the talk description on Sket. So next, we would like to talk about the future of our solution. Right now, what we're trying to do is we're trying to integrate Rebus into the support of our live migration. Our goal in this is to give some sort of fault tolerance to the VM so that we turn the solution from a reactive one to a proactive one. Imagine if you have some sort of denial of service attack that crashes only one kind of hypervisor, for example. If it affects only KVM, then with this VM replication solution, you can have a Xen server with a replica of your VM that is ready to spring back into action when your KVM server crashes. In our plan, we want to deal better with devices between different hypervisors. For example, firstly, we can implement replication of a device between different implementations. Or for example, we can replicate the device between XenQMU and KVM2, for example. Or alternatively, we want to define a model of recovering the VM from loss of a virtual device. For example, we can try to extend the virtual device model to support this. We also want to work on eventually allowing PCI pass-through to the device so that regardless of whether you are doing hypervisor transplant, in-place transplant, or migration, you will be able to plug in a pass-through PCI device and have not only full performance, but also built-in replace and recover accessibility to the guest that is running anyway. And additionally, we are always looking for more ideas on this hypervisor transplant solution. So please feel free to give us any suggestion if you have any. Um, that's pretty much it for the presentation, though. So I hope that we have some time left. So let's look into a very short demo of our prototype and how it works before we go into the Q&A. See. Okay. So here I have a system that is running Xen. First of all, I'll start a VM that runs Xen. Let's wait for a few seconds for the VM to boot up here. Okay. So the VM has already booted up. So I'll be showing that it's actually running Xen HVM. And then I'll create a small file that we'll be able to keep this file after the transplant. The VM here is running with just a very basic setup with CPU and memory, basically. Okay, so I have the file here. This just a command to to show you the date. It will update every second. And here you see I have a VM that's running on Xen. I'll run the script to start the transplant. that is in place transplant. So I'll be replacing Xen with KVM on this machine. Okay, after the script, now the transplant is actually done. So you can see that it took a very small amount of time. So I'll go into the machine again. You see that the VM is already running on top of KVM. Xen is no longer running. And now I'll connect back to the VM. Now you see that the VM has resumed running. I can read the content of the file that I created before. And basically, I've shown that I've moved a VM that's running from Xen into KVM. Okay. Saving, restoring. It's just basically telling the next hypervisor where these pages are. So like before, like I've shown before, I basically constructed a page table relates to the addresses of the physical pages. But of course, for some particular pages, I'll have to migrate them away so that it will not overlap on the region that has to do KXX later. For the open source, it's not quite open source ready at the moment because there are quite a few things that we want to clean up before we can make it open source. But we hope to do so in the future, very near future. Perf numbers. Let me show the perf numbers. So this for this figure, it's for Xen to KVM. For this figure, it's also Xen to KVM. You can see here that is there's a marker that tells you which part is Xen, which part is KVM. We do have more evaluations. Wait a second, I'll try to paste the link here so that you can read the paper. It's free to read, so make sure to check that. Yes, for now, for the problem of SRLV devices, for now we haven't gotten around to doing that yet, but we really hope to do so in the future because, for example, we think it will enable the use case of VM replication, especially in the case of you need to move a VM between different hosts and while having a pass-through device at the same time. The paper needs cooperation on gas. Yeah, we needed for now a way to unplug and replug the virtual devices. So we had a very small module in the guest that is listening for this unplug event from the host, and basically it just unplugs everything. And after the transplant, it just replugs everything, and then it works. Any more questions, perhaps? Thank you. So if there are no more questions, I'm happy to close it here. Or if you want, I can maybe talk a bit about a bit more about our solution of replicating remote-based replicating VMs between Xen and KVM. So basically, one of the challenges that we have been having is we wanted to unlink the process of replicating different CPUs. If you remember, there's a recent work about KVM dirty ring, which basically lets the different vCPUs replicate at different rates. So we've also been looking to integrate that into our solution from Xen to KVM, for example. And one of the problems when thinking about the solution is how to make sure that there's no situation where the states of two different vCPUs are not in sync. For example, you can imagine that one vCPU sends a message to another, and then you end up restoring the sender's thread on the state where the send has not happened, but then you restore the receiver thread in a state that the send has already happened. So that's also one of the solution that one of the problems that we have been thinking on, and we're trying to implement that into our solution. So if anyone have any ideas, please feel free to just contact me on because I'm not too often on RC, so I think that's it for the presentation. So I'll be on IRC at least for today. So if you have any ideas, just shoot me a message. I'll be happy to respond. Or you can contact me by mail. So that's it, and thank you for listening.